Hello everyone, I'm going to be talking about acid-base balance in health. We'll start by giving some basic definitions and then go to a brief introduction before we delve into the buffer system, essentially talking about the major regulators of acid-base balance, especially bicarbonate reclamation and bicarbonate regeneration. Generally, acids are substances that can dissociate in solution to produce an hydrogen ion. For example, if you look at carbonic acid, it is able to dissociate in solution to produce an hydrogen ion and a bicarbonate. While base, on the other hand, is defined as any substance that can accept an hydrogen ion in solution. And a typical example is the bicarbonate, which is a base, and it has the ability to accept an hydrogen ion in solution to become carbonic acid. Secondly, a strong acid is usually a type of acid that can dissociate completely in an acidic solution. For example, if you look at this hydrochloric acid, it is able to dissociate completely in an acidic solution into an hydrogen ion and a chloride anion. A weak acid, on the other hand, is only able to dissociate partially in acidic solution. And a typical example is this H3PO4, which is able to dissociate into hydrogen anion and H2PO4. You will notice that the dissociation in this particular reaction is not complete. It's a partial dissociation. That is what makes it a weak acid. And generally, when a weak acid dissociates, they usually dissociate into an hydrogen ion and a conjugate base. So the combination of a weak acid and its conjugate base forms what we call a conjugate pair. Another example of a weak acid is H2PO4, which is able to dissociate in solution to produce HPO4 and an hydrogen ion. You will notice that the reaction is a reversible reaction, in which the reaction can either go forward or backward, depending on the nature or the pH of the solution. In situations where you have a lot of acid, the acid will dissociate to produce HPO4 and an hydrogen ion, which will be released or mopped up. And in situation where you have a lot of hydrogen ion in solution, maybe an acidic situation, the conjugate base will mop up the excess hydrogen ion to move the reaction into the backward reaction in a reversible reaction, ensuring that the pH of the solution is maintained at a steady state. Before we go forward, let us talk about pH. pH is generally defined as the negative logarithm of hydrogen ion concentration in solution. In clear terms, it is defined as the degree of acidity or alkalinity of any solution, and the arithmetic representation is written as pH is equal to minus log of hydrogen ion concentration. I gave a typical example here of a solution that contains an hydrogen ion of 40 nanomole per liter. If you impute this hydrogen ion concentration into this equation, you will end up with a pH of 7.4. I want us to take note of this value because this is the pH of blood in humans. So in a patient that has an hydrogen ion concentration of 40 nanomole per liter, if you calculate the pH of that patient, you expect to get a pH of 7.4, which is usually the pH of a normal human being. Now, someone may want to ask, how do acids get into the human body? And the answer is very simple. Majority of all the physiological activities that go on in the body on a day-to-day basis from morning to evening, whether you are sleeping or you are awake, tend to generate a lot of organic acid in our body. For example, digestion of food substances, cellular metabolism like glycolysis, fatty acid oxidation, protein metabolism, including muscular activity, all of them tend to generate a lot of organic acid in our body. And this also tends to change the pH of the body if they are not immediately taken care of. It is important to note that Despite all the large amount of acid generated by the body is able to maintain the blood pH at a very steady state. And this is very important because most of the structural and functional proteins in the body are pH dependent. Think about all the enzymes, all the hormones, all the transport protein that work in the body are all pH dependent. And if anything goes wrong, such that the pH of the body is reduced or increased, all these structural and functional proteins will lose their functionality, and that might tip the patient or the person into a pathologic condition. Okay, so it is very important to ensure that no matter how much of acid the body generates, the pH of the blood is maintained at that steady state to ensure that all the proteins in the body continue to function maximally. Now, if there's any kind of failure or inability of the body to ensure that this pH is maintained, then the body is likely to go into either a situation of acidosis or alkalosis. Now, in order to ensure that the pH of the blood is maintained at a steady state, major and minor regulators of acid-base balance come into play. Their function is to ensure that the pH of the body is returned to normal in situations where there is an excess of acidity or alkalinity. They are referred to major regulators and minor regulators because of the extent of contribution they make to the maintenance of normal pH of the body. The major regulators are big, they are more extensive, and they can be found in almost all the different parts of the body. They include the buffer system, the lung and respiratory system, and the renal or kidney mechanism system. Now, these three systems are called the major regulators because they contribute a large chunk of the maintenance of regulation of acid-base balance. Now, the minor regulators are not as extensive as the major regulators. They are the red blood cell mechanism, the parietal cell of the stomach, the pancreatic and biliary mechanism, the ileal and colonic mechanism. These are essentially found in special organs of the body in which they tend to contribute to the regulation of acid-base balance in their local area and not necessarily generally. But their little contribution in that local area can have a far-reaching effect on the general acid-base balance and the pH of the body. Talking about the buffer system, a buffer is a solution that contains conjugate acid-base pair, which minimizes changes in pH. That's the basic definition. But generally, if you remember when we talked about the weak acid, that they dissociate partially to produce an hydrogen ion and a conjugate base. And the presence of both the weak acid and the conjugate base in the solution make up what we call a buffer system. And their function essentially is to minimize the changes in pH. Every time there is a change in pH, maybe there's an excess of hydrogen or excess of alkalinity, there will be a movement either forward or backward depending on the situation, whether the weak acid will go forward to produce more conjugate base and hydrogen ion, or the conjugate base will mop up the excess hydrogen ion in order to reduce the alkalinity or acidity of the body, as the case may be. Now, different types of buffer systems are present in the body, and essentially they include the bicarbonate buffer system, the phosphate buffer system, and the ammonia buffer system. It is important to know that buffer is a temporary solution to changes in acidity and alkalinity of the body. They tend to work round the clock every day of our life, whether we are awake or we are sleeping, despite all the physiological activities going on in the body, generating all the excess acid or alkalinity. The function of the buffer is to ensure that those excess hydrogen or those excess alkalinity do not harm us or do not injure us, and they make sure that the pH of the body is returned to normal. So buffer systems tend to generally provide a temporary solution to changes in pH, and it's very important that if there is any excess hydrogen ion, it must be excreted from the body in order to ensure that the person is safe. Having said that there are different types of buffer system in the body, I need to make it clear that they don't all function equally or in the same capacity to ensure that the pH of the body is maintained at a steady state. Now, the buffering capacity of each of the buffer system would depend on either the concentration of the buffer system and the relationship between the pKa of the buffer and the pH of the solution, meaning that the higher the amount of the buffer system present in the body, then the more likely that the buffer system will be called upon to respond to changes in pH of the body. Also note that every time I talk about solution in this situation or throughout this lecture, I'm referring to the blood, the human blood. So the relationship between the pKa of every buffer system and the pH of blood is also a very important factor that will determine the buffering capacity of that buffer system. I'm going to try to explain that further. Now, these are the three important points I want us to know concerning buffer system. The first one is that a buffer has its maximum buffering capacity when its pKa equals the pH of the solution in which the buffer exists. For example, in the human blood with a pH of 7.4, for example, a buffer that has a pKa that is very close to 7.4 is more likely to function better than a buffer system that has a pKa of 6.1. So if we have the option to choose a particular buffer system in any kind of situation when there are changes in pH, it will be more meaningful or more relevant to choose a buffer system whose pKa is closer to the pH of blood, which is 7.4, than another buffer system whose pH is far from that of blood. The second point to note is that a buffer is more effective in solution with pH within the 2 plus or minus 2 units of its pKa. What that means is that, for example, if you are talking about the human blood with a pH of 7.4, it will be more reasonable to take advantage of a buffer system whose pKa is within plus or minus 2 units of 7.4, meaning that a buffer system which has a pKa of 5.4, between 5.4 and 9.4, will be the best type of buffer system that can work in human blood. It does not necessarily mean that other buffer systems will not work or will not suffice. It only means that the buffer system that has their pKa within plus or minus 2 units of the pH of blood are usually going to be more effective than those other buffer systems. The third bullet point says that buffers work best when the ratio of the weak acid to its conjugate base is within the range of 10:1 to 1:10. What this means is that it's usually very nice to have a weak acid and its conjugate base to be in a very close proportion. Okay, in fact, it is better to have the concentration of a weak acid and its conjugate base to be the same in a solution, but because that does not usually happen most times, it works best for a buffer system when the ratio of the weak acid to the conjugate base is not more than ratio 1 to 10. Again, this does not mean that if the ratio of weak acid to a conjugate base is more than ratio 1 to 10, that the buffer system will not work. It only means that the buffer system will work better. In fact, they will work best if the ratio of the weak acid to its conjugate base is within ratio 10:1. Now, I want us to talk about Henderson-Hasselbalch equation, which is a very popular equation in biochemistry and human chemistry that tend to relate the pH and the pKa with respect to the amount of conjugate base and conjugate acid in the body. Now, remember I mentioned earlier that it is better for a particular buffer system to have the same concentration of conjugate base and conjugate acid. Now, if you look at this equation, Henderson-Hasselbalch equation, which says that pH is equal to pKa plus log of the concentration of conjugate base over the concentration of the conjugate acid. Now, in a situation where the concentration of the acid and the concentration of the conjugate base are the same, it will mean that this relationship will be equal to 1 because the concentration of conjugate base and conjugate acid is the same. So if you divide it by themselves, you will end up with pH is equal to pKa plus log 1. And we all know that log 1 is equal to 0. Now, if you extend the relationship, it will mean that pH will end up equal to pKa. In summary, it means that when the concentration of the conjugate base and the acid or the weak acid in this situation are the same, then you are more likely to get a situation where the pH is equal to the pKa of the solution, and this is a very perfect situation where you want your buffer system to be, because a buffer system will work best when the pKa of that buffer system is equal to the pH of the solution and the human blood in this case. So to have a very effective buffer system, we tend to ensure that, or we would like to wish that the concentration of the conjugate base is equal to the concentration of the weak acid, which usually does not happen. So if you are able to get a buffer system where the relationship between the conjugate base and the weak acid is not more than ratio 1 to 10, that will also be a very, very perfect and effective buffer system. Unlike when the relationship is more than ratio 1 to 10, then the buffer system may not be as effective as the one where you have the ratio within ratio 1 to 10, or particularly when the concentration of the conjugate base is equal to the concentration of the conjugate acid in the system, which is usually not easily possible. Now, talking about the different type of physiological buffers that we have in the body. Physiological buffers are important buffers in the body because whether the patient is sick or not, they tend to function at all times to ensure that the pH of the body is kept within the normal range of 7.35 to 7.45. Now, here I have a list of 4 important physiological buffers and their pKa. Remember from the last slide, we were talking about how the pKa of a buffer system is very important to their effectiveness in controlling the changes in pH. Now, these physiological buffers are listed here, including bicarbonate buffer system with a pKa of 6.1, hemoglobin or protein buffer system of 7.2, phosphate buffer system of pKa of 6.8, and the ammonia buffer system of pKa of 9.8. Now, all of these buffer systems are very, very important buffer systems in the body, and you will notice that they all have different kind of pKa, different levels of pKa in the blood. And then if we are going to choose or to select any of these physiological buffers in terms of their contribution to the maintenance of pH of the body, remember what you said, that the closeness of pKa to the pH of blood will determine the effectiveness of that buffer system. Now, it will appear, looking at this page now, it will appear that hemoglobin buffer system, which has a pKa of 7.2, is the best buffer system for the blood, compared to the bicarbonate buffer system, which has a pKa of 6.1. Okay, so now the important thing to note about this slide is that the relativity of closeness of pKa to the pH of the human blood is also a very important factor that will determine how effective that buffer system is. But it does not usually end there, because now hemoglobin buffer systems are usually only found within the red blood cell, while bicarbonate buffer systems tend to be found in almost every part of the body. Okay, now it is important to note that it is not only the value of pKa that is important to the functionality of the effectiveness of a buffer system. The sheer amount or the concentration of the buffer system also plays a very important role in determining the effectiveness of that buffer system. Although the hemoglobin buffer system has a very close pKa to the pH of the blood. It does not have the ubiquity of the bicarbonate buffer system, which though has a lower pKa, but it is very present in a very large amount, in a very high concentration, and it is well circulated into almost every part of the body. Now, to talk about classification of buffer system, there are several ways by which buffer system can be classified. We can classify them based on the acid conjugate base pair, for example, the bicarbonate base pair, or the phosphate base pair, or the ammonia and ammonium conjugate base pair. That will be one type of classification of a buffer system. The other way to classify the buffer system is based on their location, whether they are within the cell or they are outside of the cell. A typical example of intracellular buffer system is the hemoglobin buffer system, because hemoglobin are usually found within the red blood cell. So that will be a very perfect example of an intracellular buffer system. Whereas the extracellular buffer system are buffer systems that are found outside of the cell, and a typical example is the bicarbonate buffer system. Buffers can also be classified based on the medium in which they operate. For example, you could have a blood buffer, you could have a urinary buffer, depending on where the buffers are functioning. Bicarbonate buffer is usually found in the blood, is a very important blood buffer, while the ammonia-ammonium buffer system is usually most importantly found in the urine, so they may be classified as a urinary buffer. So essentially, there could be other types of classification of buffers, but essentially here I have based on their acid-base conjugate pair, based on their location, and based on the medium where they operate, with the examples given above. Now, to pick each of the buffer systems one after the other. The bicarbonate buffer system is one of the most important buffer systems in the body. And I explained earlier, if you remember when we were talking about the factors that determine the effectiveness of a buffer system, one of the factors we mentioned is that the buffer system with a very high concentration in the blood will make a very good buffer system. And that is one advantage the bicarbonate buffer system has. The bicarbonate buffer system has a very large concentration in the blood. It is actually said to be the most ubiquitous buffer system in the blood because of the sheer concentration which it has in circulation, compared to other non-bicarbonate buffer systems which are present in a very smaller concentration. Although the bicarbonate buffer system has a pKa of 6.1, which is relatively or comparably far from the physiological pH of 7.4, that's the pH of blood. That can be a disadvantage because 6.1 is very far from 6.4 compared to other buffers that have 7.2. But the fact that the bicarbonate buffer system has a very large amount of concentration and is almost present in almost every part of the body, that advantage will overshadow the disadvantage of a lower pKa compared to the pH of the blood. The other thing that the bicarbonate buffer system has is that usually the ratio between the weak acid and the conjugate base is usually in the ratio of 20:1. And you remember that we mentioned that the effectiveness of a buffer system is usually better and more optimal when the ratio is within ratio 1:10 or 10:1. That is the ratio of the weak acid compared to the conjugate base. The bicarbonate buffer system usually tends to have a ratio of 20:1, which may also be a disadvantage. But then the sheer amount of bicarbonate buffer system and the fact that it is present in almost every part of the body dominates, and then it shadows all the disadvantages of a lower pKa and a very high amount of ratio between the weak acid and the conjugate base. So that makes bicarbonate buffer system a very, very important major regulator of acid-base balance. Now, if you look at this equation we talked about earlier, the Henderson-Hasselbalch equation, in terms of the bicarbonate buffer system, the pH is equal to pKa over the log of the conjugate base and the weak acid. Now, this relationship shows that the pH is directly related to or directly proportional to the concentration of bicarbonate, and the pH is inversely proportional to the weak acid, which is the partial pressure of carbon dioxide. Now, what that means is that as the amount of bicarbonate increases, the pH will decrease. And as the amount of bicarbonate decreases, the pH will increase. So this shows that the pH has a direct relationship or direct proportionality with the amount of bicarbonate in the system, meaning that the higher the amount of bicarbonate in the blood, the higher the pH of the body. That will tend to lead to alkalinity. And then the reverse or the converse happens for the partial pressure of carbon dioxide, which is the weak base component of the bicarbonate buffer system. So the higher the partial pressure of carbon dioxide, the lower the pH, and vice versa. The lower the partial pressure of carbon dioxide, the higher the pH of the body. So this is also very important in terms of management of patients who has changes in their pH for maintenance and management. Yeah, so I need to make it clear that there are two major components to the maintenance of acid-base balance. There is a metabolic component and there is also a respiratory component. The lung, which is the organ for respiration, is a very, very important organ that controls or maintains or regulates the acid-base balance in the body, because it is the organ that we use to breathe in oxygen and breathe out carbon dioxide. Now, the amount of carbon dioxide present in the lung will determine the amount of acid that can be generated in the lung and by extension in the body. So if for whatever reason the lung is not able to breathe very well or is not able to breathe deeply enough and there is an accumulation of carbon dioxide in the lung, it will lead to a generation of high amount of acid in the body. Okay, and then in the situation where the lung is breathing at a very high rate, if the rate of respiration is very high, it will mean that the lung is expiring a high amount of carbon dioxide, meaning that the lung is excreting a large amount of acid in the body, and which can also have a very good or bad implication on the pH of the body, because most times when there is a change in the pH of the body, it takes the respiratory component to correct or to compensate for the changes in the pH of the body. So if there is a failure of the lung to respond either by increasing respiration or by decreasing respiration in order to control the amount of carbon dioxide in the body, then it may affect the amount of bicarbonate in the body and then affect the pH of the body and the control mechanism too. Compensatory mechanisms are a way by which the body tends to correct changes in acid-base balance in the body. For example, when there is a metabolic derangement, the respiratory components of acid-base balance tend to take up the compensation, whereas when there is a respiratory derangement, the metabolic components of the acid-base balance tends to take up the compensatory mechanism. In summary, what I'm trying to say is that when there is a metabolic problem, either in an acidotic or alkalotic condition, the respiratory component tends to come in to compensate for the metabolic derangement. For example, when there is a metabolic acidosis, the lungs tend to compensate by respiratory alkalosis, by breathing very fast. Whereas when there is metabolic alkalosis, the lungs tend to compensate by retaining carbon dioxide, which will lead to respiratory acidosis. So every time you have metabolic acidosis, the type of compensation that comes from the lung is respiratory alkalosis. And the converse also holds, such that when there is a metabolic acidosis, the lungs tend to compensate by producing respiratory acidosis in terms of retaining carbon dioxide in the lungs. Let's talk about the kidneys and their role in maintenance of acid-base balance. Remember I mentioned earlier that the function of a buffer is usually temporary. It's usually temporary. It does not provide a permanent solution to acid-base derangements. The kidney, on the other hand, is a very significant organ in the control of acid-base balance. They tend to control the metabolic component of acid-base balance, unlike the lungs, which control the respiratory component of acid-base balance. Now, knowing that the buffer system is a temporary arrangement, what usually provides the outright or the definitive control of acid-base balance is the kidney, because it has the ability to either excrete, secrete, or reabsorb any component of the acid-base balance that is defective, that is present in either a very high amount or present in a very low amount. And there are different ways by which the kidney does that. Here I have a list of several mechanisms by which the kidney ensures that the pH of the body is maintained at a very steady state. For example, we have the sodium hydrogen exchanger system. This works in a situation where you have a lot of hydrogen ion in circulation, in a situation of acidosis, where for whatever reason, maybe due to physiological activity or a pathological activity, there is a lot of hydrogen ion in circulation. The kidney is able to secrete the hydrogen ion out of the body in exchange for sodium ion in what we call the sodium hydrogen exchanger system, in order to ensure that the excess hydrogen ion are excreted from the body and the body is able to maintain the normal pH. Apart from the sodium hydrogen exchanger system, the other mechanism by which the kidney maintains acid-base balance is by bicarbonate reclamation. This is the system in which all the bicarbonates that are filtered through the glomerular filtration are reabsorbed back into the body in order to ensure that the pH of the body is maintained at a steady state. Also, there is bicarbonate regeneration, which tends to go a further step ahead of bicarbonate reclamation to generate more bicarbonate for the body in situations where there is a dire need for bicarbonate in the body. I'm going to be explaining all of that in subsequent slides. There is also excretion of hydrogen ion in situations where hydrogen ion is present in a very large amount. The kidney is able to excrete them by their combination with H2PO4, which is a urinary buffer, to excrete hydrogen ion out of the body. There is also the use of urinary ammonia buffer to excrete excess hydrogen ion in the body. So these are the different mechanisms by which the kidney is able to maintain the pH of the body and ensure that there is no excess hydrogen ion circulating in the body. So I mentioned bicarbonate reclamation as one of the mechanisms by which the kidney ensure that pH of the body does not go below the steady state. In bicarbonate reclamation, it's a physiological activity that goes on in the kidney all the time, and it is basically what happens every time there is filtration of blood through the glomerular basement membrane. All the bicarbonates in the blood that are filtered are essentially just reclaimed back into the body. I will say that again, that every time there is glomerular filtration of blood, every ion of bicarbonate that is filtered through the glomerular basement membrane is reabsorbed back into the body, and the process by which that occurs is by bicarbonate reclamation. So bicarbonate reclamation is a physiological activity that go on in the body, essentially in the kidney, to ensure that all the bicarbonates that are filtered in the glomerular basement membrane are reabsorbed back into the body. I'm going to use this diagram to explain how bicarbonate reclamation works. So, this is the tubular lumen. After glomerular filtration, all the glomerular filtrate pass through the tubular lumen, and bicarbonate is one of the components of glomerular filtrate. However, because bicarbonate is not permeable to the tubular lumen, the filtered bicarbonate on its own cannot be reabsorbed into the renal tubular cell because this membrane is not permeable to bicarbonate. Now, bicarbonate has to be broken down into carbon 4 oxide by this reaction. Now, remember I mentioned that one of the mechanisms by which the kidney ensure acid-base balance is by sodium hydrogen exchanger. This is the sodium hydrogen exchanger. So for every ion, for every molecule of sodium that is filtered that must be reabsorbed back into the body, there is a unit of hydrogen ion that is given back in exchange for this sodium ion. This is the sodium hydrogen exchanger. So while sodium filtered is being reabsorbed into the body, there is an exchange of an hydrogen ion that is pushed back into the tubular lumen in order to gain this sodium ion. Now, this hydrogen ion that is exchanged for sodium comes in contact with the filtered bicarbonate to form carbonic acid, which breaks down in the presence of carbonic anhydrase, the enzyme, to form water and carbon dioxide. Now, carbon dioxide, being a gas, is able to penetrate the tubular lumen and go into the tubular cell. Remember I said earlier that the filtered bicarbonate cannot penetrate the tubular lumen because this membrane is not permeable to the bicarbonate. But after combination with this hydrogen ion, the bicarbonate breaks down into carbon dioxide, which is able to penetrate the tubular lumen and go into the tubular cells. Now, within the tubular cell, the carbon dioxide combined with water back to form the carbonic acid through the action of the carbonic anhydrase enzyme, which breaks down back into the bicarbonate and the hydrogen ion it got earlier on. Okay, so for every bicarbonate filtered, there is one equal unit of bicarbonate that is reabsorbed. So meaning that when bicarbonate is filtered through the tubular lumen, they are reabsorbed back into the body through this process that we call bicarbonate reclamation. And you will notice that there is really no change in the amount of hydrogen ion because this hydrogen ion that was excreted comes back here and it's also secreted. Okay, so the hydrogen ion just keeps going back and forth. It keeps going back and forth. So there is necessarily no additional hydrogen ion being generated, or there's no necessarily an additional hydrogen ion being lost by the body. So it tends to just maintain the status quo and ensure that every unit of bicarbonate that is filtered is reabsorbed back into the body. Okay, so generally bicarbonate reclamation is a physiological process by which the filtered bicarbonate is reabsorbed back into the body without necessarily adding to the amount of hydrogen ion that is being lost by the body. Okay, now this is the basic summary of what I explained in bicarbonate reclamation, which can also be called bicarbonate reabsorption, because that's essentially what happens. There is simply the reabsorption of filtered bicarbonate. There is no additional bicarbonate formed, and there is no additional hydrogen ion loss. It's just simply reabsorption of the filtered bicarbonate. Now, it also helps to maintain steady state of acid-base balance, because if the bicarbonate that was filtered was not reabsorbed, that can lead to derangement of pH of the body. But bicarbonate reclamation ensures that every bicarbonate that is filtered by the kidney is reabsorbed back into the body in order to maintain a steady state of acid-base balance in the body. The third point is that there is no net gain of bicarbonate in this situation. Just like I explained, that every single amount of bicarbonate that is filtered is reabsorbed back into the body, not necessarily generating any new bicarbonate or losing any hydrogen. It's just the same bicarbonate that was filtered that is reabsorbed back into the body. And it's a self-perpetuating cycle, because it just keeps going on and on and on to ensure that there is no loss of bicarbonate in the body. As a result of that, it lacks the capacity to correct acidosis. Now, this is the situation where you are not, the bicarbonate reclamation is not necessarily providing anything special for the body. It is essentially just trying to reabsorb every bicarbonate that was filtered back into the body. So it does not have the capacity to correct. If there's any big change in pH, bicarbonate reclamation does not have the capacity to correct that change in pH. It just functions to ensure that there is a maintenance of a steady state acid-base balance in the body. Now, to go a step further, there is bicarbonate regeneration. Now, I'm going to explain this bicarbonate regeneration as one step ahead of what happens in bicarbonate reclamation. Now, in bicarbonate regeneration, look at it as a bigger intervention in terms of correction of acid-base imbalance. In a situation where a patient comes down with a serious acidosis, in which maybe there is a huge loss of bicarbonate in the body, or there is a massive production of hydrogen ion in the body, at that point, you no longer have bicarbonate being secreted through the glomerular basement membrane, because either bicarbonate is generally being lost, or there is a massive production of hydrogen ion in the body, and the bicarbonate is being used up to mop up the excess hydrogen ion in circulation. So there is usually no filtered bicarbonate to be reabsorbed. At that point, when there is no bicarbonate to be reabsorbed, the kidney now goes a step further to generate bicarbonate on its own. Okay, so the kidney goes further to generate bicarbonate on its own. And what happens is that at the tubular level, at the renal tubular level, due to the production of carbon dioxide from renal tubular cell respiration, usually when cells breathe, they produce carbon dioxide. So the carbon dioxide that is generated from the tubular respiration combines with water from the tubular cell to form carbonic acid, which breaks down into an hydrogen ion and a bicarbonate to generate this newly minted bicarbonate and supply to the body. Notice that there is no bicarbonate coming from glomerular filtration. Okay, this bicarbonate was ab initio synthesized from the renal tubular cells, from the cellular respiration of renal tubular cell. The carbon dioxide generated combined with water to form a carbonic acid, which breaks down into bicarbonate and hydrogen ion. And then this bicarbonate that is newly generated is supplied back into the body to mop up either excess hydrogen ion that is being produced that is causing the acidosis, or to improve the amount of bicarbonate in the blood in order to ensure that the acid-base balance of the body is maintained. This is essentially how bicarbonate regeneration is different from bicarbonate reclamation. Now you will notice that the major thing that happens in bicarbonate regeneration is that there is a formation of a new bicarbonate which was not primarily coming from the body. This was newly synthesized, it was newly generated. So there is an addition to the amount of bicarbonate in the body. Also, there is a secretion, net loss of hydrogen ion. You notice that the bicarbonate formed, for every unit of bicarbonate formed, which goes into the body for regeneration, there is also a unit of hydrogen ion formed, which is lost in urine. Because every time a bicarbonate ion is formed, an hydrogen ion is also formed, which is passed into the tubular lumen to combine with a urinary buffer, that's the phosphate buffer, which is then lost in urine. So in bicarbonate regeneration, the advantage it has over bicarbonate reclamation is that there is a new bicarbonate being formed and there is an hydrogen ion being lost. So those are the two major things that makes bicarbonate regeneration different from bicarbonate reclamation, and that makes it a more important system to ensure that the acid-base balance is maintained over the bicarbonate reclamation. Now, to summarize what I just explained from the diagram, bicarbonate regeneration involves de novo generation of bicarbonate by the renal tubular cells. It is not coming from glomerular filtration. It is originally primarily synthesized by the renal tubular cell to add to the pool of bicarbonate in the body. Okay, and there is also a net generation of bicarbonate, meaning that there is a generation of new bicarbonate to the pool of bicarbonate in the body. Secondly, there is a net loss of hydrogen ion, which combine with a urinary buffer. So these are the two major ways by which the body controls the loss of bicarbonate or acidosis in the body. There is a generation of new bicarbonate, and then the excess hydrogen ion in the body is also being lost. There is a loss of hydrogen ion in the urine. So the combination of these two important steps ensure that bicarbonate regeneration is a more well-positioned mechanism by which acidosis can be corrected in the body. Now, this is to explain how urinary buffer works. Remember the other time when I was trying to explain bicarbonate regeneration, I explained that for each unit of bicarbonate generated by the renal tubular cells, there is also 1 unit of hydrogen ion that's excreted. Now, the advantage of this is that the excess hydrogen ion from the body is being excreted by a urinary buffer. So generally, one of the roles of the kidney in ensuring that the acid-base balance is maintained is that it tends to provide a medium by which excess hydrogen ion in the body due to the acidosis are being excreted and pushed out of the body into the urine. So phosphate buffer is one of the very important urinary buffers, and the major function is to provide an avenue or to provide a medium by which excess hydrogen ion coming from the body is excreted and passed out of the urine. So every time there is an excess hydrogen ion in circulation and then there is bicarbonate regeneration to supplement the amount of bicarbonate in the body, the urinary buffer tends to provide the medium by which the excess hydrogen generated is being excreted in the body. Now imagine if there were no urinary buffers and there is an excess hydrogen being generated. It usually would then worsen the amount of acidosis in the body. But because there is the phosphate buffer and other urinary buffers in the body, they tend to just provide the medium by which this excess hydrogen ion is excreted in the body, and that is how urinary buffers work. So this is the explanation of what I've just explained. The urinary buffer is relatively the most important buffer in the urine. That's the phosphate buffer. Okay, the filtered phosphate combined with secreted hydrogen ion to form the phosphate ion, which is lost in the urine. Thus, pH decreases with increase in hydrogen ion secretion. So the more hydrogen ion is excreted through the urine, the lower the pH of the body becomes. So this represents the buffer action of phosphate buffer in the urine, and there is usually a net loss of hydrogen ion, which is a very good way by which the pH of the body is maintained. Furthermore, the ammonium buffer system is also a very important urinary buffer, and it functions just the same way the phosphate buffer works. Now, if you look at this diagram, in this section, this is bicarbonate regeneration going on. From cellular respiration, we have carbon dioxide combining with water to form carbonic acid and generating a unit of bicarbonate, which goes back into the body. Okay, now for each of these bicarbonates generated, there is a unit of hydrogen ion formed. Now, remember I mentioned phosphate buffer as one of the medium by which this hydrogen ion is excreted. Now, if you look at this, in situations where now bicarbonate reclamation has stopped and bicarbonate regeneration is ongoing, and at a point where the phosphate buffer is no longer available to mop up this excess hydrogen ion, then the ammonium bicarbonate buffer system comes into play. The renal tubular cell is able to generate an ammonia through this mechanism. One unit of ammonia is generated within the renal tubular cell, which makes itself available to combine with the excess hydrogen ion formed, and then combine with chloride from glomerular filtration to form an ammonium chloride, which is lost through the urine. So just like the phosphate buffer, the ammonium buffer system helps to mop up extra hydrogen ion that is formed within the renal tubular cells and make sure that the excess hydrogen ion is lost in the urine, such that the excess hydrogen ion does not go back into the body to worsen the acidosis that is commonly or generally going on. Now, this is the explanation for the urinary buffer system. So usually when other urinary buffers have been exhausted, the renal tubular cells is able to generate ammonia, which combine with the hydrogen ion formed and then form ammonium chloride, which are excreted in the urine. So generally, just like the phosphate buffer system, there is a net loss of hydrogen ion, which is a very good way of ensuring that the acid-base balance is maintained. So with that, we have come to the end of this section, and I have a couple of questions that I would like you to go through and provide your answer in the comment section. Thank you all very much for listening. I will expect to see your answers, and then we'll talk about it and discuss the right or wrong answers in subsequent sections. So question 1 says, which of the following is the primary immediate mechanism by which the body regulates acid-base balance? Option A, renal reabsorption of bicarbonate. Option B, renal control of carbon dioxide exhalation. Option C, buffer system in the blood. Option D, production of ammonium in the kidney. Whichever answer you pick, please drop it in the comment section and let us see. We will discuss them later. Question 2. Using the Henderson-Hasselbalch equation, what is the blood pH if the partial pressure of carbon dioxide is 40 mm of mercury and the bicarbonate concentration is 24 milliequivalent per liter? I showed you the Henderson-Hasselbalch equation much earlier. I would like you to impute this value into that formula and come up with an answer. Option A says 7.2, option B 7.4, option C 7.6, option D 7.8. Please drop your answer in the comment section. Third question. In response to respiratory acidosis, which of the following changes would you expect in arterial blood gas values? So arterial blood gas is usually an investigation that is conducted for people who have acid-base disorders, and usually we have the value of the partial pressure of carbon dioxide and bicarbonate. So in a patient who has respiratory acidosis, what do you expect the arterial blood gas values to be like? Option A, decreased partial pressure of carbon dioxide and decreased bicarbonate. Option B, increased partial pressure of carbon dioxide and increased bicarbonate. Option C, decreased partial pressure of carbon dioxide and increased bicarbonate. Option D, increased partial pressure of carbon dioxide and decreased bicarbonate. Please drop your answer in the comment section. Question 4. Which of the following renal processes is primarily responsible for responding to chronic acidosis? Number 1, decreased ammonium production, increased hydrogen ion secretion, decreased bicarbonate reabsorption, increased chloride reabsorption. Please drop your answer in the comment section. The last question. A patient presents with an arterial blood gas showing pH of 7.3, partial pressure of carbon dioxide of 50 mm of mercury, and bicarbonate of 24 mm of mercury per liter. Which of the following is the most likely acid-base disorder? Option A, metabolic acidosis, metabolic alkalosis, respiratory acidosis, respiratory alkalosis. Please drop your answer in the comment section. Then we'll talk about them later. Thank you all very much for listening. I will see you another time.